All right, chapter 4 on triangles. So let's first talk about an isosceles triangle. So when you have an isosceles triangle, it's isosceles, and where are we at? Isosceles, because it has two congruent sides. Those are called the legs. The third side is called the base. Okay, there's this thing called the isosceles triangle theorem, which says that if you have two sides congruent, then you have two angles congruent. So again, if AC and BC are congruent, then the opposite angles, angle A and angle B, are going to be congruent. We also call this the base angles theorem because AB would be called the base, and angle A and angle B would be called base angles. So again, be aware that in a triangle, if two sides are congruent, then two angles are congruent. Now we can extend that to equilateral triangles. With equilateral triangles, you have all three sides congruent. So if all three sides are congruent, then all three angles are congruent. And it's very simple to find the measure of each angle by taking the sum, 180, and dividing by 3. That means that each of these angles is 60 degrees. And this also works the other way around. Okay, triangle congruence. Very, 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 very important. So remember, there are 4 ways to prove triangles congruent. The first way is side, 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 showing all 3 sides of one triangle congruent to all 3 sides of another. Then there is side, angle, side. 2 sides and the angle in between. So again, side and side here with the angle in between. Then you have angle, side, angle, which is 2 angles and the side in between. Angle, side, angle. And then ignore the third angle theorem here, and then there's angle, angle, side. So now we have 2 angles and the side that's not in between. So we'll say this side. So it would not be that side, not AB, because AB would be in between. We also have our special HL for right triangles. So remember, if you can show me that the hypotenuses are congruent, so that would be PR and XY, and a pair of legs. So in each right triangle, there are 2 legs. You only need 1 pair from both triangles. Then you could prove that the triangles are congruent by HL. Once you prove the triangles are congruent, then you know that all 6 corresponding parts are congruent by this idea of corresponding parts of congruent triangles are congruent, CPTC. So when you do a proof, if you're trying to prove that a pair of angles are congruent or a pair of sides are congruent, then in the proof itself, you're going to prove the triangles are congruent by one of those 5 ways, and then you're going to prove that those angles or sides are congruent by CPCTC. So keep that in mind, right? This is how your proofs look. All right, very important. Getting into chapter 6 on parallelograms and quadrilaterals. So the polygon angle sum theorem works for any n-gon. So n is, of course, the number of sides. N minus 2 times 180 is how many, or the sum of the interior angles, sum of your interior angles. There's also the sum of the exterior angles, but that's always 360 no matter how many sides. The sides don't matter. It's always 360. A parallelogram. So this is a biggie. So a parallelogram is a quadrilateral, 4 sides, right? 4 sides with both pairs of opposite sides parallel. That's the definition of a parallelogram, okay? Notice this is the symbol for parallelogram, the sideways or the slanted rectangle. A parallelogram has 4 properties along with being parallel. First, the opposite sides are congruent. Next, the consecutive angles are supplementary. So like A and B, B and C, C and D, D and A. This is because of same side interior angles in your parallel lines. So again, if you connect it to your parallel lines from chapter 3. Then you have the opposite angles are congruent. So that would be A and C and B and D. And then you have the diagonals bisect each other. Now notice there is a longer diagonal and a shorter diagonal because these parallelograms are slanted. One of the diagonals is longer, one is shorter. But E is the midpoint of both diagonals. So it creates two equal segments on each diagonal. We also have some special parallelograms. A rhombus is a parallelogram with four congruent sides. A rectangle is a parallelogram with four right angles. And a square is both four congruent sides and four right angles. Remember that we call a square a regular quadrilateral. So in triangles, the equilateral triangle is the regular triangle. In quadrilaterals, the square is the regular quadrilateral. Notice here, this Venn diagram is showing you that a square is just the marriage of a rhombus and a rectangle. So squares have all the properties of rhombuses and all the properties of rectangles. This is your hierarchy of quadrilaterals. Very, 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 very important here. This part of it right here was actually on the OST last year. You'll see it on the practice test. So again, this idea of if you have two pairs of parallel sides, then you're a parallelogram. Four right angles, rectangle. Four congruent sides, rhombus. And if you're both a rhombus and a rectangle, you're a square. Don't forget about your kite, which has no pair of parallel sides and two pairs of consecutive sides congruent. And then your trapezoid, which has one pair of parallel sides. And then for isosceles trapezoid, the legs are congruent. Again, you probably won't see much of that. Focus more on the parallelograms. Key concepts here. So again, if you're going to do any coordinate proofs involving parallelograms, you need to know when to use each formula. So distance formula shows congruence. Midpoint formula shows whether the diagonals can bisect each other, so it might be helpful. And then slope formula is showing parallel and perpendicular. Remember, parallel is equal, perpendicular is opposite reciprocal. So use them when you need to. Okay, we'll talk about similarity and then we'll stop this video. So similarity, different than congruence. So remember, congruence, same size and shape, right? Same size and shape for congruence. Well, with similarity, you are the same shape, but not the same size. Not. You are a mini-me, right? One is smaller than the other, or one is bigger than the other. So in similar polygons, the corresponding angles are congruent, but the corresponding sides are proportional. And they are proportional by this idea called the scale factor. The scale factor is a ratio of corresponding sides. So in this picture here, down here, they have found the scale factor between BC and YZ. They did 20 to 8 and simplified it and got 2/5. You can also do 8 to 20 and simplify and get 2/5. I'm sorry, this was 5/2. So remember, the scale factor can go either way. Okay, they are reciprocals. 5/2, 2/5, they're reciprocals. But that scale factor is so important when you're talking about similarity. And again, notice when you're doing triangle similarity, it is the triangles that are similar, okay, to each other. There are three ways to prove triangles similar. Angle similarity. So you need two angles congruent. If you have two angles congruent, then the triangles are similar. You can also do side angle side, which is you have two pairs of sides proportional. So AB and QR, their ratio is the same as AC and QS, and then the angles in between are congruent. Remember, the famous picture is this. You have the triangle inside the triangle, right? So these two triangles, the small triangle and the big triangle would be similar. Be aware of that. And then you have side, 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 where all three ratios are the same. A couple common problems with your similar triangles is the shadow problem. So remember, in this picture, I have a tree and its long shadow. And then I have a person and its long shadow. So remember, you just need to create a height ratio and a shadow ratio and be consistent. If you're going to put the tree on top, then you put the person on the bottom. Same thing here with the mirror and the ground. So in this picture, angle angle they're congruent that are bouncing off, and then the Eiffel Tower is assumed perpendicular and the person is assumed perpendicular. These two triangles are similar by angle, and you'd set up the same kind of proportion. Typically, it's like this height, we'll call that capital H, and this height, and then this distance called capital D, and that distance from the mirror. Again, set up your proportions. Remember that in a right triangle, if you draw this altitude from the right angle of the big triangle to the hypotenuse of the big triangle, you create two more similar triangles. Remember that each of them shares a common angle. So this small triangle shares angle A with the big triangle, and they share the right angle. This medium triangle shares angle B with the big triangle and the right angle. So again, all of them are similar by angle similarity. Lastly, we have the side splitter theorem, which says, okay, if you know that these two sides are parallel, then you can say that this part, XR over RQ, is similar to YS over SQ. You can set up that proportion rather than dealing with the two triangles, which would involve QX, that entire side. Okay, and that takes us through chapter 7 into chapter 8, and I'll stop the video and make another one here.